Ah, you'll be all right.
But I ripped a lot of pieces out.
Because let's talk about the rest of the year. Let's talk about it. In terms of sections, there's actually not too many sections left. I know that seems weird to say, but there's not really too many sections left. We do. Let me go through the keys in the binders. Actually, we do section 4.9. We'll do section 4.9, 5.1. I know it seems weird. We've this like weird section 4.9. I don't even know why 4.9 is in chapter 4. I think it should be included with the chapter 5 stuff. But again, I didn't write the book. We have section 4.9 and 5.1, and there will be a quiz over these two sections. Okay, that'll come within like the first 1 or 2 weeks of the second 9 weeks, and then we do section 5.1, and then we do 5.2 and 5.3, 5.2 and 5.3, and I believe 5.4 before the next quiz. Oh, no, I lied. There's a quiz for this as well, because it looks like I have a 5.2, 5.3 quiz review. And then we do 5.4, and then a test. So 5.4, and then we do a test here. So 2 quizzes and a test within our first portion of chapter 5. And then, I know this seems weird, but we're going to do section 5.5. Test review. And then we do, I think it's just 6.1 and 6.2. That's a long homework. 6.1. Do we do 6.2? No, it's just 2 sections. We do 5.5 and 6.1. I feel like I did a quiz or something in 5.5. Maybe a quiz here. I'm not sure. I'll have to look at what I did last year. But then this is just our second test of the 9 weeks. Okay, just over those 2 sections. And I'll tell you right now, I make that test so it's not as much as the first test. This fourth 9, why am I going through this? I'm going through this to show you how many assessments we will really have. Then the amount of it's really kind of like 1.5 tests. You know, I try to make my tests out of like 125 points usually. This test will not be out of 125 points because it's only 2 sections. This test will be a majority of your grade for the 9 weeks. But again, 2 quizzes, test, quiz, and a test. And that's it. Like, think about this. 1, 2, 3, 4, 5, 6, 7 more homework assignments. That's it.
That's actually not very. That's weird. Because
that's not that bad.
How many days of school are left?
That's a full 9 weeks, so 45.
Mr. Maverick, how would you
45 days and you only have 7 homework assignments.
I will say this: it's all of chapter 5 is not necessarily difficult. Some of you guys are going to find chapter 5 a lot easier than chapter 4. But chapter 5 is not necessarily difficult, it's just different. Okay? So it may take some practice. Like, it may take some repetition to get the hang of things. But you'll get there. Yes, sir.
So, next week.
Yep.
Are we gonna have a quiz over 4.9 and 5?
No, I'm not gonna try to quiz before break, like that before spring break. Am I?
I won't be here.
Because camp is the
shoot.
3 days before.
Camp's next Wednesday.
Well, I'm glad we're talking about this now. Because I think I might have scheduled a quiz next week.
I would be really sad.
Oh yeah, I do have a quiz next week. I do have this 4951 quiz next week. So tell me, when are you who's not going to be here when?
Wednesday, Thursday, Friday.
So you'll be out. So I scheduled it for Thursday. Okay.
And then we go right into spring break, right?
Right. So that would be rough to wait till after spring break.
Yeah, I won't be here Friday.
But that's okay because I'm going to have it on the Thursday.
So we are having a quiz next week?
Yes. Yeah. More here. Listen up. The quiz I have scheduled for this 4951 quiz, I have it scheduled right now for next Thursday. 2 days on 49, 2 days on 51, review, quiz, next Thursday. That means, I mean, you guys leave Wednesday morning,
Yeah.
Yeah.
Well,
so it's 1, 2, 3. You do too.
yeah.
I
Would
mean,
you ever sign up for that?
you could try to take it early on Tuesday if you wanted to, but that's really up to you. You
Will
can
we
either-
have learned all of the stuff by
Yes.
then?
Yeah, we will have learned everything through the end of chapter 5, or through the end of section 5.1 by this Friday.
I would. Okay, wait. What time do we get back from camp?
12:30 on Friday at the marketplace.
Could I come here at like 1?
Yeah, here I'm gonna actually leave it open for you guys. They're gonna take their quiz on Thursday. You could take it Tuesday, Friday, the following Monday after spring break.
No.
I mean, that's a lot. That's a long time away from that.
Probably take it Tuesday.
Okay. I'll make sure to have the review ready for you guys by Friday so that you could look at everything.
Would I be able to take it during class Tuesday? Because I have other tests that I have.
Yeah, that's fine.
Tuesday. Okay.
Yeah. You guys just know. Let me know when you want to take that. I'm good with it.
Oh, we still have 2 weeks till spring break. I thought we were
Yeah,
one.
it's not this. It's not the end of this week. It's the end of next week. The end of this week is the end of the third 9 weeks.
Yeah.
It's the end of next week is the
It's
end.
just paid spring break at the end of the third 9 weeks.
Well,
That would have made more sense.
No,
Honestly.
But there's-
it would be 30 degrees, so it's spring break.
but she's saying, oh no, they're saying they should have extended out the third 9 weeks till it was the end of this. But the problem with that is, then the third 9 weeks would have been 10 weeks instead of 9 weeks. It would have actually been 9 weeks.
No, just with the spring break ahead.
Yeah.
Yeah,
Oh, no,
that's
see, then
what I was
that's-
saying.
Yeah,
It's
no.
gonna be cold either way. It's March. in
It's Ohio. I mean,
Yeah,
come on.
It should be
March
in
in Ohio.
April.
It could be 80. It could be -10. You don't know. Yeah, that's
Right.
true.
It's Ohio. Yeah, there was snow this morning. There was snow last night. It was so weird. I don't know.
70 on Sunday.
Are you looking at any other snow days? No.
No. On Friday, it did say 1 to 3. Friday night, it decided it said 1 to 3 inches of snow expected.
Oh, shot.
Nah.
Ohio is so weird.
It's so annoying.
All right. Okay, so section 4.9. Now let's think about everything that we've done this year. You know, chapter 1 was a lot of review. Chapter 2 was the definition of a derivative, right? We did finding a derivative the hard way. And then chapter 3 was all about what's the easy way? What are all the shortcuts to finding a derivative, right? We learned all the different rules, and that was the end of the first semester. And then the start of the second semester, this first half of the second semester, we've been talking about graphing. A majority of it was graphing, using the derivative. And we also talked about some optimization and that weird thing, that Newton's method thing. So what we're going to be looking at in this final chapter is really going back to chapter 3. We're going to be using a lot of our knowledge from chapter 3 in chapter 5. Because what we're looking at here is antiderivatives. Antiderivatives. Now, looking at that word, what do you think it means? Well, I've got the word derivative in there, right? But it's antiderivative. It's not taking a derivative, it's taking an antiderivative. So what do you think it means? Doing the opposite, or actually working backwards. So what our full chapter 5 is about is actually working backward. Taking a function and saying, okay, if this were the derivative, what was the original? Right? It's kind of like what you did on that quiz question, the test question where I gave you the graph and I said, this was the derivative, tell me things about the original. That's really what we're going to be doing here. There's actually a homework question, a class question, notes question about if this is the graph of the derivative, sketch the graph of the original. Not just tell me about it, but actually sketch the graph, which is kind of like what you did on your test the other day. Suppose a physicist who knows the velocity of a particle might wish to know its position. Like, think back to chapter 3. We said the derivative of position is velocity, right? If you find the derivative of position, it's velocity, and if you find the derivative of velocity, it's acceleration, right? Derivative of velocity is acceleration, and derivative of position is velocity. Suppose we knew velocity. Suppose we knew the velocity equation and I wanted to create my position equation. That we would need to work backward for, right? We would know the derivative and want to work backward to find the original. An engineer who can measure the variable rate at which water is leaking from a tank wants to know the amount of leaked water over a certain time period. That's working backward. We know the derivative and we're working backward. A biologist who knows the rate at which the bacteria population is increasing and might want to deduce the size of the population that will be at some future time. That's working backward, right? In each case, the problem is to find a function they call the antiderivative function, capital F. I don't love that they use the letter F. What you need? No, sorry. They use the capital letter F. I don't love that they use the capital letter F, but whatever, I'll use their notation. In each case, the problem is to find a function, capital F, whose derivative is a known function, right? So we're trying to create an equation. We're trying to create the antiderivative. We're trying to create a function that if I take the derivative of capital F, I get that known function, lowercase f. And if such a function f exists, it's called the antiderivative. So here's our formal definition of what an antiderivative is. A function f, capital F, is called an antiderivative of lowercase f on some interval, and we will talk about knowing the intervals and why that's important a little bit later on. We start talking about integrals. A function f is called an antiderivative of f on an interval I if you take the derivative of capital F and it will give you that known function for any x value within my interval. Okay, for any x value within my interval. Usually that interval is an open interval. Usually that's like the interval of all our numbers. Okay, so that's what we're really looking at here. Now, let me ask you something. If I have, if I want to start with, hold on, I'm going to peek at something here. Yeah. If I have f of x equals x squared, what do you think the antiderivative is going to be? What do you think the antiderivative is going to be? Like, for example, I want to create a function capital F where if I take the derivative of this, it will give me that. What do you think the antiderivative is going to be? We could come up with this. What do you think? If I take the derivative of the function and it's going to come out to be x squared.
Would be x to the third over 3.
Ooh, look at you go. He's right. How'd you know that? Was that a guess?
I just guessed.
Look at you. Oh my gosh. He's actually right. He's actually right.
Okay, all right.
Now, how?
That's a step too far.
Good guess. How do we create that? Well, I can see where you might come up with the x to the third. That's the logical guess. X to the third, right? What if I started with just the x to the third? What would be the derivative of that? 3x squared, right? But we see in our brains, well, that 3 can't be there. So what's a way to create this equation so that that 3 goes away? We divide it by 3. Or in other words, taking 1/3 x to the third. Now if I take the derivative of that, watch what happens. If I take capital F prime of x, I get 3x squared over 3. And do you see how those 3's reduce out? So this is indeed our antiderivative. That is our antiderivative. X to the third over 3. That will give you x squared in the end. Now let me ask you, what if I made this function? Plus 10. What happens to that plus 10 when I take the derivative? It goes away. So isn't this an antiderivative as well? What about what happens to minus 20? It goes away when I find the derivative. So isn't that an antiderivative as well? So I not only have one antiderivative, I actually have an infinite amount of antiderivatives. But what's the stipulation on this guy? Can it have an x value? No, it must be a constant. Okay, so here's what I'm getting at here. And this I actually just kind of went over. I just made you guess at it. So here's our theorem here. If f is an antiderivative of f on an, if capital F, that's why I don't love that you use this notation. If capital F is an antiderivative of lowercase f on an interval I, the most general antiderivative, and that terminology is one that comes up in the homework. If you ever see the term most general antiderivative, they're saying include all of those constants. How do we do that? Well, you just say plus c, where c is a constant. Yeah. If you put a plus c at the end of any antiderivative, that's saying, okay, that's its arbitrary constant. Yeah, plus 10, plus 20, minus 3, minus 10, whatever. It's just plus a constant sitting out there on the end. Okay, that is the most general antiderivative. The most general antiderivative. Take a look here. The book gives this diagram, and I really like this diagram, so I want to show it to you. I'm going to scroll down just a little bit. Yeah, I just need to see the graph. Take a look at all of those equations. Those are all of the graphs of x to the third over 3 plus a constant. I'm just changing up the constant. Now, what happens to a graph if I change the constant on the end? Like if I add 5 to a graph, what does it do graphically? Vertical shift up 5, right? If I subtract it out, it just vertical shift down. So all I'm doing is moving it up and down. Am I changing the composition of the graph? Not really. All I'm doing is just shifting it. It's one of those like rigid transformations, ones that preserve congruency of the graph. All I'm doing is changing the position. I'm not necessarily changing the makeup of the graph. So therefore, if I took the slope, I gotta get a pen now. If I took the slope at any given moment in this graph on any one of those lines, the slope would be the same, right? At any given moment, the slope would be the same, which makes sense because the derivative of each of those is the same. The derivative of every single one of those equations that you see up on the board there is still x squared. Okay? So that's what we're doing when we're adding a constant on the end. We're really kind of vertically shifting our equation up and down, not changing the composition of the graph. All it's changing is just the position. Okay, so let's work backward a little bit. Let's think about some weird derivatives, like some trig derivatives, some 1 over x and things like that. It might be a good idea to have this sheet handy. I still have this up on my my TV thing up here from before. What was this? This is just the table of all these derivatives, right? Because if you know the derivatives, you're just working backward to find the antiderivative, right? You're just working backward to find the antiderivative. Like, for example, if f of x is sine of x, if f of x is sine of x, what function, capital F, that I can take the derivative of give me sine x? Oh, okay, I like what you're doing there. Instead of saying over -1, can I just put a negative out front? Yeah. Negative cosine x. Why not just positive cosine x? Because what is the derivative of cosine? Negative sine, isn't it? If I take the derivative of cosine, it's negative sine. So to counteract that negative, I'm just going to put a negative out front. because if I take the derivative of negative cosine, it's going to give me a positive sign, exactly what I want. You know what I got to add in? Plus c. Most general antiderivative. Okay. I have f of x is 1 over x. What function gives me the derivative as 1 over x? I see it on my paper. What is it?
1, 3.
What gives me the output as 1 over x? ln of x. ln of x. Yeah? Here's my one stipulation on that. My original function, the domain was anything just not 0, right? Like look at lowercase f. My domain there was anything just non-zero, including negatives? Yes. So I have to have a way to calculate negatives in ln of x. So you know what I do to it? Put it in jail. I take the natural log of the absolute value of x because I have to be able to calculate derivatives. The domain must be the domain no matter what. Oh. Let's see. I forget about that sometimes. That's a bad habit of mine. I always forget about that plus c sitting up there. Now we will do things later on today and maybe tomorrow that will actually calculate that c value for us, but I have to be given a little bit more information. Now, take a look at example C here. I am given a general power rule, x to the n, where n is any number, just not -1. Because if it was -1, it'd be ln of x, right? So I'm given this general rule of x to the nth power where n is any number other than -1. Let's try to generalize this a little bit. Because this is exactly what we did with x squared, isn't it? Okay. So if I want capital X or capital F of x, what do I do to the power? Instead of dropping it down 1 when I take a derivative, when I take an antiderivative, what do? Add 1 to it. So this is going to be x to the n plus 1, but I have to counteract that n plus 1. I divide it by n plus 1 as well. And that's where that rule about the x to the third over 3 comes from. That's the general antiderivative. Oh, plus c. Plus c. Okay? So you're going to find now, again, we're working inversely from derivatives. Instead of dropping down 1 when I work with polynomials, I'm going up 1. Because I'm working backward. Instead of dropping down 1, I go up 1 in value. But you must always divide by that power. Okay? I must always divide by that power. I put this in the notes. If you want to print this page out, that's completely fine. But honestly, it's just the opposite of this page that I have in front of me here. Right? The only weird things that are happening is like this power rule here. The n plus 1. Notice the constant. If I take a constant of f of x, it's the same thing. You can pull a constant out of the antiderivative. If you have two functions and you add them, the antiderivative is also the sum. This is what we just talked about. Look at e to the x, man. Solid, man. If I had to write something in every yearbook, I would say, be like e to the x. Never change. Never change.
Why is it like that?
Because it is. You know, e to the x is its own thing. Just let it be. It is what it is. Okay. Be like e to the that you can take that if you'd like. When you go to sign yearbooks at the end of the year, just say be like e to the x. Never change. Or maybe you shouldn't be tough. People always write that in yearbooks. Like, why do people write never change? Like, that's so stupid.
Like, I hope.
Like, I hope you do change. Like, I hope, looking back at me in high school, I was like, oh man, I was a little Nimrod. I did not like myself. And I'm glad I changed, but yeah, that's just me. Take a look at b to the x. That's kind of a weird one there. Because if I look at my derivative sheet here, and I find the derivative of b to the x, it's b to the x ln b. b to the x times ln b, right? So to counteract the ln b, I actually have to, instead of multiplying it, inversely is dividing it, right? Because if I take this, let me just show you what I'm talking about. If I take d over dx of b to the x, our rule here, this is kind of an obscure rule. We don't use this very often. It's b to the x ln b. Isn't that just a number? Natural log of the base? Because it should be like 3 to the x. And you would say 3 to the x ln 3. ln 3 is just a number. So instead of multiplying it by the number, that's why I divide it by the number to take the antiderivative. Okay? Antiderivative of cosine is sine. We saw that, and I bet over here, yep, the antiderivative of sine is negative cosine. And then we have kind of like the inverse of our trig rules. Okay? We won't use those many, very often. It's most often like polynomials and stuff, but you'll see. Computer sounds. All right, let's take a look at this one. I'll give you a second to write that down. This looks all big and bad, but it's not too. It's not. Not that bad. All right. So we've got 4 sine x plus 2x to the 5th minus square root of x all over x. Now what I'm going to do here is piece this apart a little bit. Because I know the derivative, I can do that same thing as well. So using the antiderivative, I can break it apart. I can take 4 sine x separately from this guy here. So let's work with this 4 sine x. What's the antiderivative of sine x? What's the antiderivative of sine x? Negative cosine, right? We just saw that a second ago. Negative cosine x. And since a 4 is applied to it, I keep that 4. That's the constant sitting in front of it. So big G, oh, no, I can call this G. G of x is going to be equal to negative 4 cosine x. And you know what I'm going to do? I'm going to move this down a little bit. Because I need to manipulate this. Because I need to do something about that right side fraction before I start to reduce it, before I start to take the antiderivative. Like, here's what I'm going to do. It's always easiest if we can try something to use, or try the best we can to make it polynomial. So I'm going to separate these two pieces by uncommoning the denominator, if you will. So this is going to turn into plus a 2x to the 4th. Oh, thanks. Gotcha. And then we have, isn't this x to the 1/2? So 1/2 minus 1, you just put it in the tray over there. 1/2 minus 1 is x to the negative 1/2. Okay. All that work right there is just manipulating the x to the 5th minus square root of x all over x. I haven't touched any of the antiderivative yet. All right, so we take plus 2x to the 5th over 5. Bump it up instead of going down. Minus x to the, negative 1/2 goes all the way up to positive 1/2 over 1/2. You're always dividing it by that power, right? So because I went from negative 1/2 to positive 1/2, I divide by 1/2 as well. Okay, let's reduce down g of x now. Negative 4 cosine x I'm going to make that 2/5 plus 2/5 x to the 5th. And dividing by 1/2, isn't that like multiplying by 2? Minus 2 x to the 1/2. And if you want to make that square root of x, that's fine too. And what do I put on the end?
Plus C.
Plus c. Plus a constant. So again, all we're doing now is just working backwards. Yeah, I made that 2 radical x. That's fine. All we're doing now is just working backwards. And just like I find a single antiderivative, can I possibly find a double antiderivative?
Yes.
Yeah.
Oh my gosh.
Oh, it's not that bad. Especially when it's polynomial. Look at this. My double derivative is an x squared. It's just a quadratic.
Are we doing double derivatives in chapter 5 or no?
Yeah, double integrals. We'll call it.
I'm sorry, I meant antiderivatives.
Yeah. You'll hear me say, when I say the term integral,
Yeah.
an integral is an antiderivative. So the function is just terminology. The function is an antiderivative. Doing the process of creating the function is finding the antiderivative. The actual function is called an integral. Okay? The process is also called integration. But again, you'll figure out what that means a little bit later on. So you might hear me say those words. Just know that I'm talking about the same thing.
Okay.
All right, so what we have to figure out right now is f prime of x. Got to figure out f prime of x, right? All right, let's do it. It's polynomial, so it shouldn't be that bad. 12x to the what? 12x to the third. Bump it up. Divided by 3. Plus 6x to the second. Bump it up. Divide by the power. Now, what do I do with that constant, that minus 4? Well, you can think of it as like a power of 0. So you bump it up, power of 1, divide by 1. But that doesn't do anything. So essentially, you just tack on an x to any constant. Okay? Whenever you see a constant, you're finding the antiderivative, just tack on an x. What do I say at the end? Plus c. We want to go all the way to f. We're going to go all the way to f. This is f prime, right? We started with f double prime. Let's reduce this. So f prime of x is 4x cubed plus 3x squared minus 4x plus c. That's f prime. Let's find f. So that means f of x is 4x to the 4th, bump it up, divide by 4, plus 3x to the 3rd, bump it up, divide by the power, minus 4x squared, bump it up, divide by the power, plus cx. And you know what we do? Since we've already used our constant called c, we just add on a constant called d. Okay, just a new constant, a different constant. Now, take a look at what we have here. I know f of x is equal to x to the 4th plus x to the 3rd minus 2x squared plus cx plus d. That's a d. D. But you know what we haven't used yet? The fact that f of 0 is 4 and f of 1 is 1. Because this is a very powerful piece of information right here. F of 0 is 4. You know what that means? That means that if I plug 0 in for x into f, not f prime or f double prime, if I take 0 and I plug it in for x, the output should be 4. Here's what I mean. I know that 4 should equal 0 to the 4th plus 0 to the 3rd minus 2 times 0 squared plus c times 0 plus d. So you know what that means? D is 4. If you're ever told f of 0 equals the number, you're told what its y-intercept is. You're told what its constant, its final constant is. It's just constant. Now, like, look, the cx is not 4. D is 4. So now we can go this far. We can say that, well, now I know f of x is equal to x to the 4th plus x to the 3rd minus 2x squared. We still don't know c yet, but we do know that d is 4. We do know one other piece of information from the very beginning. It said, and I'm just going to look at it here, f of 1 is 1. F of 1 is 1. And it's going to be a struggle bus when it comes time to homework if you guys keep not paying attention. I'm just saying. That's just me, though. We got f of 1. Well, f of 1 is 1. Is equal to, now look here. Plug in 1, I get 1. 1 to the 4th plus 1 to the 3rd minus 2 times 1 squared plus c times 1 plus 4. Oh, well, that means this is 1 is equal to 1 plus 1 minus 2 plus c plus 4. Can't I solve for c?
Yes.
Right? All I did was plug 1 in for x and set it equal to 1. Okay, 1 plus 1 minus 2 all cancels. I've got c plus 4 is 1. Subtract the 4. C is negative 3. So I can end with the fact that, and this is my ending point, f of x is equal to x to the 4th plus x to the 3rd minus 2x squared, minus 3x plus 4. Okay. You can't just be told the equation to figure out what the constants are going to be. You must be given some values. You must be given some xy pairs to figure out what your constants may be. And man, if you're given the 0, that's really nice because that's telling you right away what your last number is. Okay, f of 0 is 4. That means my last number is 4. We can hold off on this one for tomorrow. All right, so we will do, how many more examples we got? We have the graphing one, which we'll start with tomorrow. And we got the motion problems, 2 of those, right? Yeah. So really just 3 more examples for tomorrow. You should get, that should probably only take me like 20 minutes. You should get a majority of the period to work tomorrow. There's not going to be a work day on section 4.9. And then we'll spend Wednesday and Thursday of this week on section 5.1, and then we will do a work day on Friday. Okay? That's a lie. What am I talking about? Today is Tuesday. All right. 5.1 will be on Thursday, Friday. The work days will be Monday, Tuesday, Wednesday, Tuesday, Wednesday next week.
Okay, I have a question. So
Yeah.
why did we put the 0 in first? Like, could we done the 1 first? Would it?
You could have, but the 0 is such more of a powerful statement that you know D is 4 right away.
Okay,
Like
it's a y-intercept.
because it's the y-intercept.
So if it's f of 0, that would be the y-intercept.
Use that one first. Always.
Okay.
Does that make sense?
Yeah, because I just didn't know why we started with that.
Yeah. You could have started with the other one, but that would have told you, it would have left both C and D in the equation.
Yeah.
And that would have been good.